All right, everybody. Hope you're doing well. What we've been talking about is time series and forecasting. And just to very briefly get us back into the mindset, in case you haven't been, we talk about time series. What we're talking about is we're talking about a series of observations for one unit of observation over a long period of time. And we'll call these Y, the series Y, and we'll call time T. And so we have like y1, y2, it's period 1, period 2, dot, 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 until we get to the last period, y big T, maybe you want to call it. And we're just talking about the relationship in particular between y, whatever it is, and time. And we're not doing a causal analysis for this class, so that's not what we're involved with. We're just looking at the relationship between y and time for the purposes of trend estimation and forecasting. And that's what we're really looking at. We've done some smoothing stuff already with moving averages and some naive forecasting, some looking at measuring forecast error. Right now what we're going to look at is trend estimation. So without further ado, let's do it up. Trend estimation. Okay, so we have gained a lot of tools from regression. Regression analysis, for those of you who are not familiar with regression analysis, I highly recommend you watch the videos from before. But with regression before, we had a model that looked like this. Y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus dot 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 plus beta k xk plus epsilon. And we had one y, which was our dependent variable. And then we had all these different x's, lots of x's. One y, lots of explanatory variables. And what we were trying to do is kind of make we were talking about partial correlations, right? How do x1 and y move together? How do x2 and y move together? What might that look like? Well, it might be x1 might be education and y might be income, and so we might want to know about how income changes across people. This is, we were doing a cross-sectional analysis. We were looking across people to see how education affects income. But what we're doing now is a time series analysis, basically. We're not going to look at education and income. What we're going to do maybe is income over time. So we want to estimate, let's say, first of all, we want to estimate, so what we're going to do, we're going to use regression to estimate trend. If you recall, trend is one of the ways in which and a variable could be related to time. There's also seasonal relationships, seasonality. There's also irregular relationships, which is just random noise, and there was also cyclical relationships. But trend is a gradual shift, and so that's what we're talking about here. We're talking about gradual shifts in the value of a variable over time, and so that's what we're going to look at. So let's say, for example, we want to estimate a linear trend. What does this look like? Well, what we do is we have y equals beta 0 plus beta 1 times t plus epsilon, where t is the period. Right, so year 1, quarter 1, if you have quarterly data, year 1, quarter 1 would be t period 1, year 1, quarter 2, year 1, quarter 2 would be t equals 2, and so on and so forth. The year 5, quarter 4 would be, what would that be? That would be 20, and so on and so forth. And so t, you plug that in, and what you're essentially doing now is you're estimating a linear relationship between t and y. You're estimating this line. This is beta 0, and the slope is beta 1. You just use regression techniques, and we'll go through, if you look at the practice problems, I'll go through some examples in a later video to show you what this looks like in Excel and to show you how you might estimate this. But that's what we're doing. So you might have, remember, we might have like a time series data, with a time series plot that might look like this, right? And then this is estimating the linear trend, is what that underlying line is. It's trying to figure out, okay, well, there's some noise going on here, clearly. That's why we have this distance here, and this distance here, and a distance throughout because of that. But there's some underlying trend. Well, let's capture that. Now, what else can we do with this? Well, one other thing we might have is a different pattern of growth, right? So we might have growth that looks like this. Over time, y starts out small and goes whoop like that. Or over time, y is increasing at a decreasing rate. So it might go whoop. You might think that these are relationships that we have going on. There are some other models we can use with these. Okay, so let's say we want to measure what's called a quadratic trend. Again, using our regression techniques, this is not that difficult to do. Our left-hand side variable is again just going to be y, and that's going to be equal to beta 0 plus beta 1 t plus beta 2 t squared plus epsilon. And so we plug in our period, and then we plug in the period squared, and we plug in our data, and that'll estimate a quadratic trend. The interpretation here is important, right? Because beta 1 greater than 0 is going to mean increasing, and then beta 1 less than 0 is going to mean decreasing, meaning our estimate, right? We're going to estimate using b1, and here, that's our estimate. Beta 1 is the parameter in the population that we're trying to estimate. But if our estimate of beta 1 is greater than 0, and we might conclude that beta 1 is greater than 0, then that means that there's an increasing trend. What about beta 2 though? Well, if beta 2 is greater than 0, then it's increasing at an increasing rate. Alternatively, if beta 2 is less than 0, well, it's increasing at a decreasing rate. And down here, ditto. If beta 2 is greater than 0, that means it's kind of pulling out of this dive, right? So that means it's decreasing at a decreasing rate. It's decreasing by less every time. And if beta 2 is less than 0, it's decreasing at an increasing rate, meaning it's getting further and further down, right? It's going, plummeting. This one right here is kind of like, it's more like, it might be leveling off, or yeah, like leveling off like that. Okay, so that you can use a quadratic term to try to capture curvature in the trend, and this might be useful for some growth models. In addition, though, we have one more that's very useful for a growth model, where you might think that something is growing exponentially. What does this look like? Well, this is called an exponential trend. And the underlying model is this. For any period, yt is going to be beta 0 times beta 1 raised to the t times epsilon. Okay, now, this, as it's modeled, we can't plug that into a regression, so we can transform it. What we do is we take the log of both sides. We switch pens here so you can see. Before I explain, though, you can just see that for t is 1, then beta 1 is just being raised to the first power. For t is 2, then beta 1 is being raised to the second power. It's squared, and then it's cubed, and then it's raised to the fourth power, and so on and so forth. And so t is the power to which it's raised. And so that could be, it can grow. Things can grow that way. So we take the log of both sides. Log, it's ln. Log. You get log of y sub t equals log of beta 0 times beta 1 to the t power times epsilon. It turns out that based on what you can do with logs, because of what they are, if you have, this should all be in parentheses, if you have a log of a product, you can that's the same as, so the log of x times y is log x plus log y. That's just a rule of what you can do with logs. So we can break this up into log of beta 0 plus log of beta 1 to the t plus log of epsilon. Define that again, or we can break it down a little bit further. because if you have log of a to the b, that's the same as b times log of a. So we have t times log of b beta 1. Okay, now this looks a little bit more like what we've used before with regression. It takes a little transformation, but this is how we estimate an exponential trend. What we do is we define a few things. We're going to let y squiggle equal log of y, beta 0 squiggle equal log of beta 0, beta 1 squiggle equal log of beta 1, and epsilon squiggle equal log of epsilon. And then we have our model, which just has a lot of squiggles in it now. Y equals beta 0 squiggle, y squiggle equals beta 0 squiggle, plus, sorry, not this, plus beta 1 squiggle times t plus epsilon squiggle. And now you just estimate beta 0 squiggle, beta 1 squiggle. And what we do then, if we do this, is you can interpret b1 squiggle, which we've estimated, as the rate of growth per period, as percentage change from one period to the next. And that's what that does for us. And if something's changing by a fixed percent rather than a fixed amount, then a method like this will help with that. Okay, now one of the problems with estimating time series is that our assumptions on the error term are almost certainly violated, right? One of the assumptions we had on the error term was that epsilon, the errors were independent. This is almost certainly violated. It's especially likely to be violated if we have seasons. Estimating trend helps pull that out, right? Because what we're doing is we're pulling out the time component. But with seasons, we have correlated errors, right? Every first quarter error, or we have correlated residuals at least. Every first quarter residual, if you haven't deseasonalized the data, is going to be correlated with every other first quarter residual because they're all first quarters. They all have something that's that's not included in the model in common. Okay, so if we have a seasonal component, we can account for it in a couple different ways. And the way I'm going to talk about right now is a pretty straightforward way. It's called the dummy variable approach. So this is the dummy variable approach to estimating trend with seasons. One of the problems with not including seasons is you might think that there's no trend. You might reject them. You might find that there's not a significant trend, even if there should be a significant trend, because your errors are going to be so big because your seasons are just driving, they're bouncing the data all over the place, and so you think that you're not getting a very good estimate. But one of the things we can do is we can account for the seasons through dummy variables. Now, if you're not real comfortable with dummy variables, I recommend you watch. Or if you're totally unfamiliar, you should watch the video. If you're a little comfortable, then you should be fine. A dummy variable is just a variable that equals 1 if something is true and 0 otherwise. And usually we use D to indicate it, D, I, or D1, D2, something like that. Okay, so let's say we're looking at quarterly data, and we want to use quarterly dummies. Well, what we do then is we define, so if you have, with K periods, you define, K seasons, sorry, not periods, seasons, you define K minus 1 dummies. So we have quarterly data, K equals 4. We're going to need 3 dummies. It doesn't really matter which 3 you choose, but the convention is usually to leave the last one empty. So let's see. We'll define like this: D underscore quarter 1 equals 1 if first quarter, 1 if quarter equals 1, 0 otherwise. We'll define D underscore quarter 2 equals 2 if quarter equals 2, 0 otherwise. can see why I'm choosing to do quarters instead of months. But you can do the same thing with months. You just need 11 dummy variables, one for January through November, and then you leave. You always need to leave one omitted. D quarter 3 equals 1. Sorry, this should be 1, not 2. 1 if quarter equals 3 and 0 otherwise. Okay. And then you don't have a fourth quarter dummy. The reason you don't have a fourth quarter dummy is that otherwise you'd have a collinearity problem with your intercept term. What that would mean is that you wouldn't be able to, if you have collinearity, your data doesn't know how to, or the algorithm doesn't know how to fit the data properly. Most statistical software packages will tell you that, hey, you have a collinearity problem. You have a perfect multi-collinearity problem, so you should fix that. If they don't, then you just will get a crappy estimate of everything. Okay, so we have these 3 dummies. We still want to estimate trend. So what is our new model? The new model, the seasonal model, looks like this. Sorry, I have a bad habit of clicking my tongue. Apologize. YT is equal to beta 0 plus beta 1 times D quarter 1 plus beta 2 times, I'll put these in parentheses, I suppose, times D quarter 2 plus beta 3 times D quarter 3 plus beta 4 T plus epsilon. Now, how do we interpret this? Well, first of all, this will give us, beta 4 will give us our B4 will give us our trend. So that's good. We will have solved the seasonality problem, assuming it's a linear seasonality problem. This assumes that we have it, that the quarters are just adding or subtracting a fixed level amount. But that's fine. That's not a great assumption, but fine for our purposes for now. How do we interpret this stuff? Well, what do we get for the expected value of YT given T and quarter equals 1? Well, that's going to be beta 0 plus beta 1 times 1 plus beta 2 times 0 plus beta 3 times 0 plus beta 4 times T, and the expected value gets rid of epsilon as well. So, for first quarter data, we have beta 0 plus beta 1 plus beta 4 times T. What about second quarter data? The expected value of Y given T and quarter equals 2. Well, that's beta 0 plus beta 1 times 0 plus beta 2 times 1, because we're in the second quarter, and that's how we define that, plus beta 3 times 0 plus beta 4 times T. And again, these cancel out. So we have beta 0 plus beta 2 plus beta 4 times T. For quarter 3, the expected value of Y given T is going to be, I'm not going to go through the whole thing. I encourage you to plug stuff in there until you feel comfortable with it. It's going to be beta 0 plus beta 3 plus beta 4 times T. And then for quarter 4, all of those are zeros. All the dummies are zeros. And so we just have beta 0 plus beta 4 times T. And so we can interpret this. How can we interpret this? Well, essentially what inserting these dummies does is it allows us to have, well, we have different intercept terms, right? So the slope term is the same. So that's what we've done. We've managed to isolate the part that's trend, and that's the same in every case. But what we've done now is we have one intercept term, which is this combination, 2 intercept terms, 3 intercept terms, and 4 intercept terms. This is our quarter 1. You can think of beta 0 as like the quarter 4 baseline. Whatever your omitted one is, beta 0. And then beta 1 is the quarter 1 bonus over the baseline. Beta 2 is the quarter 2 bonus over the baseline. Beta 3 is the quarter 3 bonus over the baseline. And those can be negative too, so you can have a negative bonus or a penalty, but this is what we've done. We've said, in case we have seasonal data, is something like this. So let's say we have data that looks like this. It goes up, up, down, down, up, up. Oh, well, it should keep going forward. Let me fix that. So it goes, let's see, it goes up, up, down, down, up, up, down, down, up, up, down, down, up, up. And so we have a data set that looks something like this. Connect the dots. It's good practice for my pen drawing, which is not very good, as you can see. But how can we interpret this? Well, what inserting those dummies does is allows us for each of these, quarter 1, 2, 3, 4, quarter 1, 2, 3, 4, quarter 1, 2, 3, 4, quarter 1. So I'm estimating quarter 1 with an intercept like here. And I'm estimating quarter 2, which is this one and this one and this one and this one, with an intercept here. The slopes have to be the same. We've restricted the slope to be the same because what we've tried to do is isolate a trend separately. What we've allowed ourselves to do is to have something like different intercepts, right? We're estimating 4 lines now. One for just the baseline and then one for each dummy that we included. So 4 would be here maybe, right? And those slopes should all be the same. Introducing the dummies allows us to make it, to reduce the noise by allowing us to fit quarters together. So we're treating all the quarters like they're either getting, some kind of fixed bonus for being in a particular quarter. That's good. That allows us to, to more, to know what's going on, to get a better forecast, to more accurately estimate the data, get a better fit to our model, and count for seasonality when estimating our trend. One of the things that we implicitly assumed here is what's called an additive decomposition model. And that's, kind of clearly the case. We used addition, and we basically said that our observation for each time period was based on a trend effect plus a seasonal effect plus an irregular effect. Now, there's good reason to believe that this might not be a great model. In some cases, we might want to use a multiplicative decomposition model, and that requires a little bit more in-depth analysis to get rid of the seasonality in that case. And next time, that's what we'll talk about. We'll start and we'll go through time series decomposition and how to take out the seasonal effect in a multiplicative model, and then how to estimate the trend, and then to make a forecast and re-seasonalize it. Here, we can do that already. If you want to know what a quarter, once you estimate this, if you want to know what your estimate is going to be for year 5, quarter 4, well, you just, you set these dummies equal to 0. This one's going to be 0, this one's going to be 0, this one's going to be 0. And then you plug in year 5, quarter 4 would be 20 in there. Right? And then you can, you take your estimates. It's going to be B0. Y20 is going to be B0 plus this times 0, this times 0, this times 0 plus B4 times 20. And that's your Y hat. That's your best guess. So we can already do that. We can make forecasts with that. Okay, so as I said, next time we'll talk a little bit more about deseasonalizing things. If you have any questions, as always, shoot me an email at jjdelaney@ualr.edu or post a comment and I'll be in touch. Thanks, guys. Talk to you again soon. Bye.